key to this section, conservative vector fields and independence of path, is if the vector field is conservative, you can do a lot of neat things with that. So that's the key. So we determine if you're given a vector field, see if it's conservative. If it is, two things you get. Matter of fact, three later on, but two here directly that you get for free. One, if the vector field is conservative, then the line integral is said to be, if you apply we'll talk about in just a minute, the fundamental theorem of line integrals. If the vector field is conservative, I can apply this theorem. And then that means that I can get the line integral very quick, hopefully. I can get the line integral without even computing the line integral. I can simply find the potential function and evaluate it. If the vector field is conservative, very powerful. If the vector field is conservative, then I can skip integrating with respect to the direct line integral. You know how you found ds and then, or you found f dot dr? Well, you can skip all that. The other second neat thing is that if the vector field is conservative, then we say that the line integral is independent of path. That simply means that if the vector field is conservative, it doesn't matter where you travel, going from one fixed point to another fixed point. You may travel a long distance or you may travel a short distance to get from one point to the other point, but the same energy will be exerted in either path. So in other words, if the vector field is conservative, the line integral will always be the same if I'm evaluating the line integral from one fixed point to another fixed point. It doesn't matter what road you travel down. Doesn't matter which road you travel down. If it's conservative, then the value for the line integral is always the same, from one fixed point to another fixed point. If they change the fixed points, then obviously you get different value for the line integral, okay? So the key to all of this is if the vector field is conservative, wow, I can do some neat things. The third thing that we'll get for free, and he puts that, Larson puts that in a theorem, and that is if the vector field is conservative, then if the path is closed, if it's a closed loop, the line integral is automatically zero, right? No energy, right? In other words, I'm talking about energy, but basically no work. Or the work that is displayed is said to be consumed. So we first talk about a very classic theorem, the fundamental theorem of line integrals. 1, 2, 3, 4. You have seen thus far 4 fundamental theorems in mathematics in your life, from the first grade to now. Calculus 1, yes. From the first grade to Calculus 1, you have exhibited and dealt with 4 fundamental theorems. One is actually 2 in 1. But there's a fundamental theorem of, oh, let me say this. I won't tell you the name of it. I'll give you the example. When you were in grade school and they gave you a number and they asked you to write that number as a product of its primes. You remember that? Take the number 27, right? You'll say 1 times 3 times 3 times 3. Because 3 is prime. 1 we say is either prime or composite. It has both, natures. Take the number 18. So you say 18 is, what are its primes? One times 2 times 3 times 3, right? We say that any number can be written as a product of its primes. Even if that number is a prime, then it's written as the product of 1 in itself, right? So we all remember that, right? What is that called? Well, here's the thing. We did that, but they didn't tell us in grade school what that was called. And then it's pretty neat because I was helping my fourth grader last year, and I said, Zion, this is a classic theorem in mathematics. Yeah. And I said the proof thereof was very difficult for the mathematician who actually proved this, around 1793. It's called the fundamental theorem of arithmetic. That's the name of it. That's, it's like the idea, that's what they're teaching kids, but they're not telling the kids exactly what that is. And you start taking discrete math, abstract algebra, number theory, you run into that particular theorem and you have to prove it. The proof is in the book, whatever textbook that you're using for number theory or numerical analysis, it comes up there as well. The fundamental theorem of arithmetic. What's the second fundamental theorem? And then give me an example. Do you remember? It was in algebra. There was a fundamental theorem of algebra. Do you remember that? What about the factorization theorem? Remember that? You remember that? The factorization theorem is a corollary. It comes out as a consequence of the fundamental theorem of algebra. That was proven by Carl Friedrich Gauss for his, he had a dissertation and he wrote it when he was 21, 22 years old, and he actually proved that. And of course, you could imagine that the whole world just erupted in grand applause from China all the way to the States when it was heard that that theorem was actually provable. The fundamental theorem of algebra. What does it say? Okay. If they give you a polynomial, let's say the polynomial looks like, give you something simple, x squared minus 9. Can you factor that? What are its factors? X plus 3 times x minus 3 in two sets of parentheses, right? What tells you can do that? The fundamental theorem of algebra. That's what I'm talking about. Right? You hopefully I want you to guess that, right? That's what we're talking about, it, right? The fundamental theorem of algebra says that. The fundamental theorem of algebra says that if you have a polynomial of nth degree, it can be factored at least one time. In other words, there should be one zero, whether real or imaginary. Right? The factorization theorem says that of the n minus 1 terms that are left, you can factor those repeatedly until you have sets of parentheses times sets of parentheses and say this is the product. Even if you have x squared plus 9, it also, based on the fundamental theorem, has also factors. X squared plus 9 would have the zeros, even though they're complex or they're imaginary, x plus 3i parentheses times parentheses x minus 3i. Right? That's because of the fundamental theorem of algebra. So the key is that if you're taking arithmetic, you need to run into that fundamental theorem of arithmetic, because by it, everything else that you do in arithmetic is based on that. In algebra, everything that we do in algebra is based on the fundamental theorem of algebra. But if they never tell you that, then you have no real recourse in terms of what are you doing, why am I doing it? You're just playing with numbers. You're just in the playground just playing with numbers. Right? And that's no fun, just playing with numbers. There has to be a goal, purpose to why I'm doing this. Right? So then in calculus, what's the fundamental theorem of calculus? What does it say? That's right. That's right. You can always evaluate an integral based on its antiderivative, right? And you say that when you evaluate the integral, it's tantamount to saying that you can evaluate the last term minus the first term because all the middle terms begin to cancel out when you do the Riemann sums. And you saw that, hopefully you saw a good example of that in chapter 9 in Calculus 2, when you had to determine whether or not a series, if it was convergent, if it was a telescoping type series, you saw how those middle pieces collapsed, and all you had left was the first guy and the last guy. Well, that's still based on the fundamental theorem of calculus, right? There's another fundamental theorem. Basically, the fundamental theorem of calculus, that part says that when I integrate, I can actually evaluate, right? I can say that the value of the integration is the last limit, the function evaluated at the last limit minus the function evaluated at the first limit, right? So you can plug in A and B, and that's how you basically do all your integration. That's the fundamental theorem of calculus. There's a part two. What is the part two of the fundamental theorem of calculus is? Oh yeah, it's in that one. The fundamental theorem of calculus part two says what? Talks about the nature of the derivative and the integral, that they are what compared to each other? Or basically some type of inverse, right? So that if I take the derivative of the integral, I get the function, the original function back over again, right? And then if you have complicated limits, then you have to do a du to actually get the result. If it's just not going from a to b, if it's going from like a to 3x squared, you have to then take the derivative of that 3x squared and plug that into the answer. Right? So if I have the derivative of the integral, I get the inner function, or if I have the integral of the derivative, still the same thing, I get the inner function. Right? That's the fundamental theorem of calculus part two. So you come here, and we have a classic theorem that gets you through the rest of the studies of mathematics from this point onward. So you go and if you take any of the other courses in mathematics, from here all the way to graduate school, the fundamental theorem that we use here to get you through all that is the fundamental theorem of line integrals. It says that if the vector field is conservative, then I can, here, if f is conservative in R, and then the values for the vector field is m times I plus n times j. If m and n are continuous in x, y, then the line integral can be equal to the evaluation of the potential function. That's all that is. I evaluate the potential function, and the way you evaluate the potential function is the same way you would evaluate an integral. I take the upper limit, evaluate the function on that, the answer to the integral, minus the lower limit function evaluated there. But the function here that you're evaluating is the potential function. So basically, no need to calculate the integral of f dot dr. If f is conservative, find its potential function and just evaluate it on the limits, and you're done. Right? Pretty cool. Let's see. Okay, show that f is conservative and verify that the value of, why is that way over there? It goes together. Verify that the line integral is the same for each parametric representation of C. Let's see. All right. So first it says to verify that f is conservative. So from that, m is equal to x squared minus y squared, and n is equal to negative 2xy. So we have the partial of m with respect to y, that's equal to negative 2y, and the partial of n with respect to x is equal to negative 2y. So yes, it's conservative. So if it's conservative, so here are the steps. Check to see that capital F is conservative. Step 2, if so, find the potential function. Step 3, evaluate the potential function, evaluate the limits at the potential function. Okay. So from this vector field, we're going to find the potential function. We're going to evaluate this guy. Remember, we changed I to dx. Then it's a minus sign there, so minus 2 times xy dy. So I'll do the integration. The first integral, the integration with respect to x. So this is x to the third over 3 minus xy squared minus, evaluate the second integral with respect to y. So that becomes 2xy squared divided by 2. That's just minus xy squared. Okay, plus some constant. All we need, little f of xy, is x to the third over 3 minus xy squared. So I'm just going to evaluate here the line integral at this potential function here using the limits of integration. Now what I have to do, notice that the potential function is in terms of x and y, but here the paths are in terms of t. Right. So no problem for part I. Let's see if I can rewrite it. Come down here. So that first guy, I got it on paper instead of going back and forth. This first one is the first path. It's not equal. Semicolon is r sub 1 of t is equal to ti plus the square root of t j, and then the path goes from t goes from 0 to 4. Good. And the potential function that we had, we just found, was f of x y is equal to x to the third over 3 minus x y squared. Right there. Yep, that's right. So this line integral of f dot dr is equal to, here, this x to the third over 3 minus x y squared. That's evaluated from 0 to 4, but that's with respect to t, so I'm going to convert this f of xy to a function of t using this. X is equal to t, right? And y is equal to the square root of t. See that? This is x times I, this is y times j, right? So using that, this guy becomes, the x is t, so that's t to the third over 3 minus x times y squared. X is t, so minus t times here, the square root of t squared. So this guy is t to the third over 3 minus t squared. So that's what I'm evaluating here, t to the third over 3 minus t squared, evaluate those guys from 0 to 4. So we get 4 to the third over 3 minus 4 squared. So that gives us 64 over 3 minus 16. And this is 64 minus, is that 48 over 3? So what is that, 16 over 3? So now the only work that we did was to find that potential function. Now let's see how easy it is to do part 2. Part 2, the curve, it says C sub 2 is given by the path R sub 2 of W is equal to W squared I plus WJ here, where W goes from 0 to 2. So this tells us that X is equal to W squared and Y is equal to W. See where we always get X? This is X times I, and then this is Y times J, right? So that's where I'm getting that from. So f of x, y, which we found to be x cubed over 3 minus x times y squared, this is equal to, here, w squared to the third over 3 minus x, but that's w squared, times y, that's w to the second. So we get w power raised to power multiply the powers, that's w to the 6th over 3 minus w to the 4th. So this line integral is equal to its, since it's conservative, is equal to its potential function evaluated at the limits of integration. That goes from 0 to 2. So this is 2 to the 6th over 3 minus 2 to the 4th. So this is 64 over 3 minus 16, and we get the same value, 16 over 3. So if you're looking for the line integral, if the vector field is conservative, find the potential function and then just simply evaluate the potential function at the limits of integration, and you get the value for the line integral. Yes, sir. Yes, sir. If you kind of look at both of those functions, they're actually the same. It just because that difference. Yeah, if you look at how it's working itself out, let's go back up here. This is t, and this is the square root of t. It's somewhat the same nature. This is w squared and w. And so look at, they got t and the square root of t, so this goes from 0 to 4, but then this guy is w squared to w, it goes from 0 to 2. It's really the same path. Yep. So that's, I mean, he's just doing a little trick there. Again, and you're right, if I know that the vector field is conservative, then the line integral is going to be independent of path if the points are fixed that I'm evaluating from. And now for this guy, it looks like they're different, but they're actually the same. Because here, one is the square root and the other one is squared. So, yeah. Yeah. Yes, sir. Good question. Let's look at this next one. All right. So here it's the same thing, let's see what happens there. So I'm going to determine whether or not this vector field is conservative. So m is x squared. The partial of m with respect to y is 0. N is equal to y. The partial of n with respect to x is 0. So it's conservative. So since it's conservative, we're going to find the potential function. So we're going to take the integral of x squared dx plus the integral y dy, and this gives me here x to the third over 3 plus y squared over 2 plus some constant. And so we take the potential function, let's call that little f of xy. This is x to the third over 3 plus y squared over 2. Now for c sub 1, f of xy is whatever x is to be cubed. So this is x is t. So this is t to the third over 3 times, or plus, and then y, it's t squared to be squared. So that's going to be, if I can just write that, t to the fourth over 2. Now for this one here, f of x, y is equal to, it says x cubed. X is sine theta, so this is sine cubed theta over 3 plus, it says y to be squared. This is sine square theta, so that to be squared, that's sine to the fourth theta all over 2. Yes, sir. Yes, sir. No problem. I'm just going to just scroll up like that, but that information is still there. So for part I, we look for the line integral of f dot dr, and we found the potential function for that one to be t to the third over 3 plus t squared over 2, and we evaluate that from 0 to 1. So that's just 1/3 plus 1/2. So that gives us 5 over 6. Now the same thing should happen here for the second one. This line integral f dot dr is equal to its potential function, since the vector field is conservative. Here we evaluate this from 0 to pi over 2. So sine of pi over 2 is 1, so this is 1/3 plus here 1/2. 5 over 6. Right? Okay. No, that's just the answer. I forgot to write in there class assignment, but I'm pushed for time now, so I got to try to cover these 2 sections because the test is tomorrow. Yes, sir. Okay. So here it says evaluate this line integral using the fundamental theorem of line integrals. Basically the same question before. What they're saying is if you see this question, they're saying, check to see if the vector field is conservative. If the vector field is conservative, then you can evaluate this line integral at the potential function by evaluating the potential function at the limits of integration. So m is equal to 2x plus 2y. That implies that the partial of m with respect to y is equal to 2. N is equal to 2x plus 2y. This implies that if I compute its partial with respect to x, I get 2. So it is conservative. So if it's conservative, then we look for the potential function. This is the integral of 2x plus 2y dx plus the integral of 2x plus 2y dy. So this gives us here x squared plus 2xy plus 2xy plus y squared plus c. So we claim that the potential function is x squared, get rid of one of those guys that's repeating, plus 2xy plus y squared. So we compute the line integral evaluated here at the potential function is x squared plus 2xy plus y squared, evaluated here negative 1, 1 to 3, comma 2. So basically, we evaluate at the top, so x is 3, y is 2. So here we have x is 3, so this is 3 squared plus 2 times 3 times 2 plus y squared, y is 2 to be squared. Then it's minus here at now the points negative 1 and 1, so x is negative 1 to be squared minus 2 times negative 1 times 1 minus 1 to be squared. So here, this evaluation goes back to the fundamental theorem of calculus. Minus plus 12, excuse me, plus 4 minus 1 plus 2 minus 1. So that cancels out. We have 16, what is that, 25? Everybody with me? Okay, good. Now we want to look at this idea of a line integral being independent of path. You kind of saw some of it here. That is, if it's independent of path, you get the same line integral for 2 fixed points. But there is a clause that's necessary that we should note before we can go there. And, yes, sir. Yeah. Yes, sir. Mm-hmm. Yes, sir. is, you know how you evaluate an integral?
Yes, sir.
That's all we're doing. So this is f of x of a y of this is a comma b.
I was going to have that negative parentheses 1 squared. If we would subtract all of that.
I did. I just ran the negatives through. It's negative times brackets, but I just put the negative through there. So
Okay, but that negative 1, but the 1 squared should not be a negative 1 squared. But it could change. Like that's
no, this is. Oh yeah, that's x. Yeah, negative 1 squared. Thank you. Yeah. Yes, sir. Yeah, very good. This is.
Could change.
Well, no, it doesn't. Yeah. Good.
Just put it in kind of drop it.
Yes, sir. Yeah, sorry about that. Yes, sir. So this idea of the line integral being independent of path is somewhat twofolded. We say that the line integral is independent of path if every time you measure or you calculate the line integral from two fixed points, the value of the line integral is the same, if and only if the vector field is conservative. And quite naturally, the components of f must be continuous to be able to compute those partial derivatives. Right? But in order to see this, in order to see that the line integral is independent of path, we got to talk about the region. And so the region by which I'm evaluating the integral, we say the region has to be connected. Now, I think we got a graph down here to illustrate connectedness. We say that the region is connected if I can always take a smooth curve, and that one smooth curve can connect 2 points in a region without breaking the smooth curve up. So look at this first illustration where it says R sub 1 is connected, but R sub 2 is not, because if I go and connect points A and B, this smooth curve is actually broken up into 2 separate regions. So I want to be able to have that curve, this path that I'm using, to be contained within the region itself completely in order to connect the points. So if we have connectedness for the region and f is conservative, then we say that here the line integral is independent of path. If it's independent of path, it doesn't matter how you travel. If I'm traveling, if I'm doing that, I get the same value for the line integral. If I take the scenic route and get lost, but as long as I'm still within that region, we get the same value. Yes, sir. Yes, sir. The work is the same.
What's going on that makes that line so much longer there?
Just in one path, if it's shorter, then the movement is faster, the velocity. And if the path is longer, then the particle, the velocity is moving a little bit slower to actually get the same value. That's all. Yes, sir. Yep, that's the only thing that's happening. Yes, sir. It was physics in this regard, my friends, that we encountered on Saturday when we took the kids at the church to Alabama Splash Adventure. And they got this old 20-year-old roller coaster called Rampage. Has anybody experienced it? I hate it. Great use of physics. Oh boy, man, there was great curvature. There was momentum at its best. Look, man, we were able to calculate. You remember we had, I think, a chapter or two ago, we talked about the maximum increase or the minimum decrease, that type of thing. I felt it. We got to this highest point, and they drop you. And look, I never do roller coasters, and I'm saying, why am I here with these crazy kids, right? You know. Yes, man. So I got off, and I said, I'm never getting back on. The kids said, let's do it again. Y'all go right ahead, you know. And then I was concerned because, you know, my little son, he's on one of those, and I'm like, when I was riding with him, he was right in front of me. I could check the seat belt and all that and make sure this thing got to be tight. Because look, man, you know. And so I'm seeing him when I'm on the ground. He's going up. I'm like, did they check his seat belt, man? My wife is going to kill me if something happens, you know. So when he got down on the ground and he said, let's do it again, I said, no, let's go, you know. Let's get in the water. So let's see. Let's work a problem here and see what's going on. The theorem says that if F is continuous on an open connected region, and the neat thing for you is that the problems that we're given, the region will be connected. Something even more fascinating is there's the class that I had where you spend considerable time determining whether or not the region is connected. And there you have to use a lot of limits and proving and trying to find some epsilon and they call those accumulation points. Can you find accumulation points within the region? And you find all these points and you find all these balls around these points to say if they cluster up or if it's dense. And just makes you scratch your head a whole lot. You know, man. Oh, boy. So that was fun, right? Yeah, I don't know. Well, the neat thing for us is that the problems are kind of rigged for you, so the regions are automatically connected for you, so that's good. So the main thing you're checking now is to see if F is conservative. If it is, then no matter which values they give you, it's going to be independent of path if we're still talking about the same two fixed points. Okay, let's see. Oh, this third one that I want to add, if the vector field is conservative, I can use the fundamental theorem of line integrals. Secondly, if the vector field is conservative, then the line integral is said to be independent of path. And then number 3 here, which is important, that is that if the curve is closed, if it's a closed loop, going a continuous loop, automatically the line integral is 0. Let's see. So here, evaluate the line integral along each path. Hint, if F is conservative, the integration may be easier on an alternative path. Here when they say that, if it's conservative, this alternative path basically use the fundamental theorem of line integrals. That's what they're saying. They're kind of begging us to do that if you have that. So here, that is, find the potential function. So here, let's check the partial of m with respect to y is 2x, and the partial of n with respect to x is 2x. It's conservative. So I need to find the potential function. So I integrate 2x y dx plus the integral of x squared dy. So I get x squared y plus x squared y plus c. So we use the potential function f of little f of xy to be x squared times y. You see here, they are evaluating different paths that's given. But we're traveling through the same two fixed points. Right? So what we do for the first one, notice that here x is equal to t, then y is equal to t squared. And then for that second path, x is equal to t and y is equal to t to the third. So for part A, the line integral is equal to the potential function evaluated on the limits of integration goes from 0 to 1, but that's in terms of t, so we convert the x's and y's to t's. So x is t, so this is t squared times y, and y is t squared, so this is t, oops, it goes from 0 to 1. This is t to the fourth, evaluated from 0 to 1. We just get 1. For part B, the line integral is equal to x squared y, evaluated from 0 to 1. But here x is t, so that's t squared. And then y is t to the third, and that's raised to the third. I'm sorry. I'm looking at that too much. This is times y. Y is just t to the third. So this comes out to be t to the fifth. That's evaluated from 0 to 1. I forgot. We just get 1 for that one as well. Okay. So what's the difference between what we're doing now compared to the problems we just did before? Not too much of a difference. It's still the same approach. The key is that I want to check to see if the vector field is conservative. If it's conservative, find the potential function and evaluate the integral, evaluate the potential function at the limits of integration. Right? We just pick up something for free here now that if you know that the vector field is conservative, then the line integral said to be independent of path. Now, you want to show for both methods, the good thing is if you know that it's independent of path, you're supposed to get the same values, right? That's the thing, supposed to get the same values. Now, you know, if you're on the test and you get two different values, then you got to determine which value is the right one, right? You don't know, you know, whichever one you think is right, you put that for both answers. Well, you show the work. Hopefully it works out. So. All right, so now they give us this line integral, and they're going to give us different paths. A would be this path, part B, a different path. Let me show you. Part B is this path right here, and then part C is this path there. And this guy is closed, so no work there, right? The line integral is equal to 0, you're done. So that's a closed loop, right? It's closed. So if it's closed, And oh yeah, by the way, we got to make sure that F is conservative. So I skipped that. But go back to the first part, and we'll show that. So here, the partial of M with respect to Y. Remember, this is M, so this is 2Y. And the partial of N with respect to X is 2Y. So it is conservative. Do you see that the potential function, if you can look at that, the potential function, do you see it is xy squared? The potential function is xy squared. And after a while of doing this, you kind of get it, right? So are you with me here that little f of xy is xy squared? Who doesn't see that? And if you don't, then I'll just work it out real quick. Everybody see that? Okay, good. So when they talk about independent of path, here's the cool thing. And see, it comes up a lot, even in electrical engineering, when you have a circuit that's traveling through a circuit board. And if it's possible to determine independence of path, there's no need to calculate going from, say, for example, one resistor to another, or from that resistor or a diode to a transformer. If it's independent of path, you calculate what's happening in the beginning, what's happening at the end, and you're done. Right? But the key over in there is being able to determine whether or not it is independent of path. Because sometimes they're not going to give you those functions in terms of a vector, so you have to use something different. Differential equations comes into play there. So since we did determine that this guy's independent of path because the partial derivatives are the same, we check that criterion. So all I have to do is don't even worry about evaluating. Look, here's what they're saying. This, I've seen it where it's like C sub 1, and then this part from 3, 4 to 4, 4 is like C sub 2. As you go here and there, it's all connected region. And so you can evaluate the line of growth from 0, 0 to 3, 4, plus the line of growth from 3, 4 to 4, 4. That'll be the same as evaluating from 0, 0 to 4, 4, because it's independent of path. So we just bypass 3, 4, right? So let's see. So this line integral remember it's that xy squared that's evaluated from 0, 0 to 4, 4. So this is just 4 times 4 to be squared. That's just 4 to the third, 64. Now let's look at the next one. So it's still the same. This was still the same problem here. So it's still the same line integral of y squared dx plus 2xy dy. And so this guy is still the, I think, was it xy squared or xy squared? So this guy, they give us the loop here. We're going from -1, 0 to 1, 0. Now it's not defined as a closed loop, but we're going to get 0 y because here y is 0 for both. So here we get x is 1 times 0 to be squared minus -1 times 0 to be squared, and we get 0. I think it's Dr. Goldman in physics when he dealt with the nature of the conservative force field, and I think there where they evaluated work, he gives a very neat example of what that is. And he said years ago when he was moving, and he hired two guys to move his furniture from his apartment to his house, and he said that when they returned back to his apartment, he'd pay them for the work that they did. And so, did anybody hear him give this story? It's pretty neat. Yeah, you know, they make a complete loop, right? So they go from the apartment to the house, then they go back to the apartment. And he says, well, here, according to the conservation law of energy, conservative vector field, you made a complete loop, and so the work that you exhibited is zero. So he said, I guess I don't have to pay you anything. So, well, the class laughed. He said, no, I think he said he gave him $20 and a case of beer or something like that, whatever, you know, he told them. Now, I know where I'm from down in Selma, look, man, you got like a 3-piece from Kentucky Fried Chicken, man, and a case of beer. That's all those dudes need, man. You know, you don't need anything else. That'll answer a whole lot of problems. Well, that's not good. But and this is indeed closed. So there. That line integral is 0, and so you're done. If you see that is a closed loop, then you know automatically if it's closed and if the vector field is conservative. If it's not conservative, then you may get something. It might not be 0. This guy right here. Yes, sir. Yeah, independent of path means this. If you know it's independent of path, you can ignore the path. Just evaluate the endpoints. What's the path? The path is based on that guy right there. I didn't even touch that. That's the power of a conservative vector field. If it's conservative, right, it's independent of path. If the region is connected, right? You just plug in those numbers here. The numbers, it starts from -1, 0. Here, x is -1, x sub 1, right, y sub 1. And then you go from x sub 2 to y sub 2. That's all we did, right? So you evaluate at the top, going back to just the fundamental theorem of calculus, right? X is 1, right, times y, 0 to be squared. Then minus x is -1 times y squared, that's 0 to be squared. You get 1 times 0 is 0, minus 0 is 0, right? And so again, you know that. Nothing from nothing leaves nothing. Okay.
So on the left side of that graph is x1, is x1, y.
Yes, sir. X sub 1, y sub 1. Okay. All righty. All right, let's move on. Oh, I forgot there was another guy. This guy is closed too, right? Still the same problem, part D. It's closed. I really want to give you this one to do by yourself. I think we may be in good order. I think I can finish the last section in 30 minutes, from 9:30 to 10. So let me give you that time to work this problem. Here, this is in the space x, y, and z. So how do you determine if the vector field in the third space is conservative? What do? Use the curve, right? That's right. So see if the curve is equal to 0, and then if it's 0, find the potential function, and then do your evaluation. Let's see what you get. let me, you should be able to get that one. Let's move on to the next section. F is conservative. You do get that. You get the curl of F. It comes out to be 0. The potential function, little f of xy, little xyz, excuse me, comes out to be, very neatly, xyz. So for this one, we evaluate xyz from 0 to 4. This is 2t squared, evaluated from 0 to 4. So we get 2 times 4 squared, we get 32. And then for this guy, x, y, z, evaluated from 0 to 2, is t to the 2, 3, 4, 5. That's evaluated from 0 to 2. We get 2 to the 5th. That also gives us 32. Okay. Very good. So, let me turn that off.